seminar series. As you know, this will be run until June. We have got funding to have 10 seminars. So today is the first seminar of this series. Some logistics, as always, after the seminar. For 1 hour, we have flight refreshments, and not only postdocs and PhDs are more than welcome to spend 1 hour with the speaker to have a more informal chat about everything. If you have not, please sign the attendance sheet. It's for legal reasons as well, not just so we know today. And yeah, it's my great pleasure to introduce Rémi. Rémi is originally French, but he's now American. Lives for many years in the United States. He did his PhD in material science at Georgia Tech, became a professor at NYU, but like another person I know, preferred not to be teaching and went to Sandia National Labs, and is now.
Oh, I love the teaching. I like the teaching.
I preferred not to. And yeah, where he's a distinguished member of the technical staff, and he's also the recipient of the Keith Brimacombe Medal and Sandia's Postdoc Association Distinguished Mentorship Award in 2020. So,
all right. Well, thanks. Thank you for the invitation. So today my story is about through my research, giving you some examples of like how I see the field of material science changing, and how it's changing in terms of like how we as scientists, I'm sure there's like chemists, there's like material scientists, there's like physicists, we can start bringing our own expertise in the field of machine learning as opposed to doing the inverse. Okay. And is it working? Oh, it was working before, and now it's frozen. Maybe I need to click on this. Let's see. All right, cool. And so what's interesting is, again, we're entering like a new era where really we have to work at the intersection of like many fields. 10 years ago, 20 years ago, when I was a grad student, you would basically specialize in one field. And now what you see, and I'm sure you guys see that in your research, you have to be a man of many trades or woman of many trades. Meaning you have to know a little bit of theory, you have to know a little bit of like data science, you have to know a little bit of like the experiments. And we're like basically, entering this point where we are the convergence of like these like different fields. And so if you look at least the way I was taught material science back in the 90s, late 90s, it was very sequential. The way you think about material science is you try to basically link process to structure to property. Again, very, very sequential. And at each step, there's like, some data that's going to flow from process to structure. There's going to some data that's going to flow from structure to properties. And at every single step, you're going to have to do some interpretation. You're going to have to do, most of the time, some misinterpretation of that data. There's going to be a lot of data you're going to be collecting. Some of that data is going to be corrupted. Sometimes it's not. And it's a very tedious process, okay? But we're really entering an era where now you can rethink this like paradigms from like the 90s, but more in terms of like machine learning terms. And you can now, superimpose on top this like, process structure property. I'm sure you guys, read about this in like many material science papers. You can reframe this in terms of like 3 actionable verbs that make sense when it comes to like machine learning: detect, prognose, and adapt. And the idea is like you can detect fingerprints associated with your process structure property paradigm. You can prognose the effect of this fingerprint on the process, on the structure, and the property. And you can use that knowledge to basically adapt your process. And where machine learning comes into play is basically taking the material scientist and the data scientist out of that loop so that you can spend more time doing the detection, the prognosis, the adaptation, as opposed to like focusing on the data analysis. And most of the examples I'm going to be giving you today are basically in that mind frame, okay? And so really, at a very high level, when you think about the way we are applying machine learning to material science, physical science, chemical science problems, the idea is like we want to use machine learning, different types of like machine learning algorithms to detect patterns in the data that we have. Most of the work that I do is like I care about microstructure. So like the idea is like using different types of like machine learning algorithm to kind of like fingerprint your material and then use that fingerprint to do some inference on material's performance. Okay. And so if you look at like the zoology of machine learning, it's a very wide west. Okay, there's like many different types of techniques ranging from like, supervised learning techniques where you can do stuff like classification. So again, identifying like patterns, doing regression, so linking inputs to outputs. There's stuff related to like unsupervised learning. So this is more for like, data visualization of like complex data sets. So kind of like moving beyond our own cognition, clustering. So again, like, thinking about like patterning. And you also have like reinforcement learning. So this is more about like, how do we make this decision based on like all the data we can collect? But the issue is, again, with like materials, chemical, and physical sciences, like most of the tools that you can access out there, out of the shelf, they're not necessarily like adapted to what we do. Okay, and so the trick is like, and the main question that Ari would like to kind of like cover with you today is like, how do we school machine learning algorithm to learn these fingerprints in various types of data sets? If they can be multimodal, it's even better. And how do we link them to materials performance? So again, if you don't work on like material science, you can still like kind of like, take this question and template to like exactly what you do. Okay, so the first keyword and action is like, how do we learn something from our data and how do we link it? So I'm going to go over like a few examples. I have like 4 examples. We see how to do in time. Maybe I'll cover 3, maybe I'll cover 4. But to kind of like just give you a flavor of like some of the stuff that you can do. And the first topic I want to cover is what I call super resolution, or you can super resolve data. And the idea is like, can I teach a machine learning algorithm to take a crude description of a material system and kind of like coming up with like a super resolution of that system, okay? And so the topic I'm going to be talking about for this is we are applying this to like mesoscale simulation of microstructure. Okay, and primarily I'm going to be talking about a technique which is called like crystal plasticity. So we use crystal plasticity to basically simulate the deformation of polycrystalline system. Okay, and from this type of simulations, you can infer stress and strain, basically, and how it's being distributed into the microstructure. And so when you do this type of like mesoscale simulation, the computational cost associated with like this type of simulation is pretty substantive, and it exponentially explode as you increase the resolution. So what are the implications when you do some types of like machine learning application? Is most of the time, if you look at like what's available into the literature, if you want to simulate or if you want to do or develop some like machine learning algorithm to kind of like speed up simulations at that resolution, that means you need to have you need to have like training data at that resolution. Okay. What I want to show you is that actually you can teach a machine learning algorithm to take data at like very low resolution, which is cheap to compute, and being able to like predict what would be the response at a high resolution. So that's kind of like a way you can speed up what you do. Okay. So at a very high level, the secret recipe is we have a description of like a microstructure. So we have like a mesh at some high resolution. I'm going to call n. Okay. And I want to pass that through like some neural network operator to basically predict the stress and strain at that high resolution, except that I only want to use low resolution data to train that neural network. Okay. So again, this is a very crude resolution of that problem for which I have like stress and strain, but it's also very cheap to calculate. So I can generate like a lot of like data at low resolution And now I want to basically able to like predict what would be the solution at like some randomly high resolution. And the secret recipe is basically you need to embed the physics directly into the neural network, okay? So there are two approaches for this. The first one is, I'm going to say it's a very classical approach now in machine learning, and people have been calling this like physics-informed neural network. So for example, there's like George Kardanakis at Brown University who's published like many papers on this, kind of like the godfather of like pins. And the idea is you basically embed the physics into the loss function of your neural network, okay? So you can embed information in terms of like the stress and strain. You can embed information in terms of like the constitutive equation that you're trying to simulate. And you can embed things related to like the governing equations, okay? This is called basically like a soft constraint on the neural network because it is built in the loss function that you use to train the neural network, okay? But there's actually like another solution, and which is like some of the stuff we've been developing recently in my group, which is what we call in this case like equilibrium conserving operator, where now we take like some of those constraints that we had in loss function and we embed it directly into the neural network, okay? So if you think about a neural network are very good at predicting either like scalars, or they're very good at like predicting vectors. Everything else, they're not doing so great, especially if we're talking about like physical fields where you have to like satisfy, you know, symmetry, compatibility, etc., right? So you can basically play a little bit of like, you know, a couple of games in terms of like, you know, differential calculus. So again, if you accept the fact that like neural networks are very good at like predicting vectors, then you can play some math where you can transform a vector into like what looks like a stress field, again, by just playing some tricks in terms of like differential calculus. So if I take that vector and I define my stress tensor as a function of like partial derivative of that vector, that tensor is going to be symmetric by definition, and it's going to satisfy exactly the equilibrium condition. Okay, so it's kind of like a little trick that we played. And we did the same thing for like the deformation field. Again, if you accept that the neural network is very good at like predicting scalars, the definition of like a deformation field is it has to be, you know, compatible and derived from like some displacement field. Turns out that vector is going to be kind of like a, you know, a displacement field. And so by just like playing this, now you can derive operators, like almost like a neural network block, that you can tag along to like your favorite neural network architecture. So again, in our case, we have a high resolution microstructure for which we want to predict the stress field and strain field. In this case, we developed like a fairly simple, it's called like a UNet architecture. And the reason we developed or we use that architecture is because you have like multiple layers, and each layer is kind of like meant to capture different length scales associated with your stress field and strain field, okay? And at the end of our neural network, we tagged on our now new operators, one for the stress, one for the strain. And I'm going to show you also comparison where we did pins. Again, pins is like where you incorporate all the physics, but in the loss function instead, okay? So, and these are the type of results that you get. So again, we used this type of information, so low resolution data for training. And we're trying to predict, in this case, something at like a higher resolution. So here we just double the resolution in X and Y. Okay, so this is the ground truth we're trying to predict. This is the data that we use for training. Okay, and here I'm showing you 3 solutions. So equilibrium conserving operator. So where, again, you embed the physics directly into the network. PIN, which is more like a soft constraint type of implementation. And TFNO, which is something that you can get out of like the literature where people have been using this for like quote unquote high resolution prediction. And so the only thing I want to point out is like, first of all, these 3 techniques works pretty well. You know, at like the naked eye, it's not that bad. The second thing I want to point out is if you look at like the echo solution, we tend to do like a much better job when you have like basically sharp discontinuity in the data compared to like a PIN or the TFNO. And actually, it makes sense if you start thinking about the way this network was penalized in terms of like the way you train it. Because again, the physics is quote unquote only in the loss function, as opposed to here, we're going to satisfy everywhere the equilibrium for the stress. We're going to satisfy everywhere that the fact that deformation is going to be compatible. So why is that? The reason is actually like fairly simple. If you look at like basically the way the information is being predicted by the neural network, or like the different types of architecture, and if you look at like, you know, the distribution of frequency that you have into your data, when you embed the physics directly into the network using our echo simulation, you tend to like basically represent much better the high frequency data that is lost when you have like low resolution data, because again, you don't have enough resolution to capture the high frequency data, but which is also lost when you basically embed the physics, quote unquote, only in the loss function. Okay, so that's kind of like, you know, a natural thing that you gain by embedding the physics directly into your network. You're able to like kind of like, quote unquote, naturally capture the high frequency data that you otherwise lose, okay? And so it becomes very powerful because now we have a tool where we can start generating a lot of like low resolution data, which come as a cost X, okay? And you can predict something at like a fairly high resolution, which sometimes costs like 100 times more. Okay, so what does it mean when it comes to like doing, you know, any machine learning exercise? Is now I can generate like, you know, a very broad variety of configuration when if I only had at my disposition some neural network architecture that could only work with high resolution to high resolution, I would be very limited in terms of like the amount of like high resolution training data that I could generate, okay? So it's kind of like a way for you to kind of like speed up what you can do, simplify what you can do by just playing the simple trick of like embedding the physics directly into the neural network. So again, I don't know what you guys are working on, but you can probably start to translate and map out what you guys do and do this type of application, okay? And we call this like super resolution because, again, here's it's another example. So we have like some microstructure with like some cavity. And you can imagine as you increase the resolution, the discontinuity that you have at the cavity is going to be more and more, you know, resolved right and localized right at the boundary between the cavity and the matrix, right? To the point where if you had like an infinitely fine mesh, you would have the exact solution, okay? And so actually, if you look at like predictions, so again, here in this case, we train our data on like a 64 cube data. We try to basically predict what you would get from 128 data. So this is what we're trying to emulate. But this one still has some like numerical error just because of the mesh, okay? But actually, if you look at like the type of results that we get with our echo solution, we basically obtain in terms of like the equilibrium of like the stress concentration, something that like approaches machine precision. So you can think about this as like you have like a super resolved mechanical solution that you don't even get with like very fine meshes, okay? So that's the first example I kind of like wanted to show you is like we can take algorithms that exist out there, embed the physics, and get something that we could not get before, okay? So the second example I want to talk about is how do we develop different types of like machine learning architecture to do prognosis of performance, okay? And so specifically here, it's more in terms of like an additive process, okay? So we printed some microstructure. So like this is an example of like some microstructure that you have. From print to print, you're going to have some like variability in terms of like the microstructure that you print, okay? It's something that you have like inherently when you print something. And so that means when you do the testing on these parts, you're going to have some like variability into the response, okay? And the variability comes from obviously like uncertainty due to the measurements, but it also comes from uncertainty into the microstructure and also uncertainty in the properties of the different phases themselves, okay? So in this case, we use like this like thermoplastic, binary thermoplastic, and each of the phase that we print, depending on like the time you let it sit on the shelf, you may have like some variability in terms of like, you know, the response. And it's kind of like maybe like a fingerprint of like the aging. And so the idea is like, can we develop some like machine learning strategy that would be sensitive to like the variability of the microstructure, that would be sensitive to the variability in like the properties of the materials themselves, and that would also be sensitive to the experimental uncertainty. So how do we do this? It's kind of like similar to like the previous problem. So you're probably familiar with like what a perceptron is. So it's kind of like the building block of like any neural network. And the way a perceptron works is you have some input. So here I'm going to say I have like strain 1, strain 2. So the strain in each of the phases, okay? And I'm going to have like some weights and biases. And then, I can basically relate or learn some function f based on the weights and biases, okay? But actually there's like something that you can do that looks like this, but that would be sensitive to the microstructure, that would be also sensitive or know something about the physics you're trying to model. And in this case, it's kind of like you just reconsider what that perceptron looked like, but now you make it look like what you know. In our case, we make this perceptron look like a binary composite. We know how to model a binary composites in terms of like homogenization. So, homogenization in terms of strain, in terms of stress, energy consistency, and traction continuity between the two phases. And I can use these rules now to make like what I would call like a micromechanics informed multi-layer perceptron, where now like the weights and biases are directly informed from your constitutive equations, from your equilibrium equation. Okay, so again, you start with like the concept of like, what mathematicians and computer scientists have done, but now we kind of like project that into our own field. And so conceptually, it has like some benefit because now you have also a sense of like interpretability associated with like your neural network, okay? So let me just like decompose how that neural network looks like. So here in this case, I'm going to train the neural network to like simulate the effective elastic properties of some composite. So the output node of the neural network is going to be the effective property, okay? If I go one layer below, so again, I'm looking at like that building block, I can say, I can decompose that like gray homogenized block into a binary composite where I know how to like define the weights, and now the bias is going to be like some like a vector. And so now the function is going to be a function of like these weights. And then I can go, a layer deeper. So now I'm going to break down the orange and the purple into like, other types of binary laminate composite. And then I can assign the properties to like each of these composites. So technically speaking, what we've done is something that like, people in micromechanics have been doing for like 20, 30 years. And they call this like an L-rank laminate. Except we kind of just like automated this, and we kind of like translated this like L-rank laminate theory into like what looks like a neural network, okay? So the advantage of this is it's a very powerful technique because the way you train it only on elastic data, which is cheap to generate. So the way to feed the beast is initially you start generating some elastic data for some combinations of like what would be the properties of the matrix, what would be the properties of the inclusion. And you can use your favorite sampling scheme, it doesn't really matter. Then you can use your favorite numerical solver to calculate the effective properties. And that takes, actually that's what takes the most time. And then you can use that data to train your network, and it takes about an hour. Okay, so again, I'm training the neural network only on elastic data. So, 270 hours in terms of like periodization, actually it's not that much time. And this is what like the training looked like. So again, interpretation is like one of the benefits of that type of technique, where, you randomly seed your neural network initially, you build your cost function to kind of like minimize with respect to the elastic properties. And at some point, it's going to converge to some like surrogate microstructure. The advantage of that like surrogate microstructure, so again, that's your neural network. But you can think about this as like an equivalent microstructure with like much fewer degrees of freedom than you would have with like the microstructure you're trying to emulate. And then once you have that, then it's extremely powerful. So you train your network on like elastic data, and then you freeze all the weights and biases, so the W and the N. And then you can use your network as like a very simple mechanical solver. but with like a lot less degrees of freedom. And the reason it works is because the weights and biases, as they are distributed through the networks, or another way of saying this is like the way that surrogate microstructure works. The surrogate microstructure learned the mechanical interaction between the different phases, and those mechanical interactions are reflective of the same type of distribution of like mechanical interaction that you would have in your microstructure you're trying to simulate. So as an example is here I'm showing you predictions for, you have like some composite with some like inclusion, and here we have like a temperature ramp across across the z direction as a function of time. And as you increase the temperature, the particles are going to expand and they're going to start to plastify the matrix. Okay, so you're going to have like a nonlinear response. So again, the network has been trained on elastic data only. The only thing we had to give was the constitutive behavior of the inclusion and the constitutive behavior of the matrix. Okay. What you see here is the marks, the X marks are results that you would get from direct numerical simulation. So think about finite element. In our case, we use like fast Fourier transform. It doesn't matter. And the lines are basically for like different types of like boundary conditions, the predictions from our neural network. Again, only trained on elastic data, but now it's able to predict the nonlinear response. Okay. What this graph is not showing you though is like the computational gain that you get. Okay. So if you use the classical direct numerical simulation, again, FEA, it takes about 10 hours per simulation, but just like running this neural network on my laptop would take like less than a second. Okay, so here it basically opens up opportunities in terms of like doing fast predictions in terms of like the response. So how does it relate to that problem? So in this case, you know, we wanted to print many different types of coupons where, you know, the microstructure would be slightly different, and that's going to result in like variability into the microstructure. The way we did it is you just have to now kind of like modify that neural network to account for the fact that like now it's not just like one surrogate microstructure, but it's a family of surrogate microstructures as seen by the network. Okay. And then you use like, you know, a classical like, you know, negative log likelihood loss function to train your network. And now instead of like predicting just the effective properties, now you want to predict a probability distribution function of properties. Okay. And so this was for us kind of like a demonstration of like what we could do. So we printed the blue phase, so just like a simple test coupon. We printed the red phase, simple test coupon, and we measured experimentally the nonlinear response. Okay. Then we did 30 tests on like these like different types of like microstructures. Because the microstructure changed from like coupon to coupon, you would have like a distribution of responses. And again, all of these are experimental data. Okay. And then what we did was we took the nonlinear response of the red phase, the nonlinear response of the blue phase, and we fed that into our variational neural network. Again, that was trained on elastic data, and trying to see if we would like, you know, basically predict the variability that you would see in the experiments. And this is the type of results that you get. You know, pretty decent. We have like, you know, we're basically able to capture with, you know, there's still some errors, but I would argue it's still pretty good. We're able to capture the variability in the response due to the variability of the microstructure when the network, again, has only seen elastic data. So very powerful. And now you can start doing some statistics in terms of like, you know, distribution of local stress field and local stress field at like, you know, different macroscopic strain, and then use that, for example, for like doing diagnostic on like the parts that you printed. Okay, so very powerful. So that was the second example. So now I'm going to shift gear and give you another example, which is not going to be computational, actually, which is going to be experimental. And the idea here is how can we accelerate data acquisition using different types of like strategy using machine learning. Okay. And primarily I'm going to be focusing on atomic force microscopy, which is like a technique that we use to like measure features in nanometrology. Okay, especially like in the semiconductor industry. And so if you're familiar with that technique, again, you have like, a beam with like a tip, and you come and you can basically probe your sample. It's kind of, the way you measure your surface features. But there are some trade-offs. When you use that type of technique, there's like trade-off between speed and precision. So the faster you do your scanning, it's a scanning probe microscopy technique, the faster you take this, it's going to be at the detriment of the precision. Which means if you want to generate like a lot of data, it's going to be at the detriment of resolution. And if you want to generate like a lot of throughput, that means you're probably not going to be able to like sample a lot of like different types of samples and coupons. And so therefore, it's going to be at the detriment of like generalization. Okay. So how do we use machine learning basically to kind of like solve or address some of these trade-offs? And the problem we're trying to solve is basically, I would like to take a very fast scan, which has like a lot of artifacts. So what you see, you have these like line scans, corruptions, you have these, like what looks like dust particles. You have this like, blur to a point where you have like, what's called like a clean target. So historically, when people do this type of like scans, they have to spend a couple of hours, basically do like post-processing of these images to kind of like remove some of the corruptions that you have on your AFM data to come to this. And on top of this, you also have to use like generally like a very slow, fast scan to get to something that looks like this. So from a machine learning perspective, you can reframe that problem in a very simple way. The idea is like you would like your machine learning framework to basically learn the corruption. How do you learn the corruption? You take your raw scan and you remove the clean target from it, and you get your corruption. But there's still an issue here. If I want to do this to train any machine learning network, I need to have a lot of data. If I need to have a lot of data, that means one of you guys, especially like postdocs or interns, are going to spend hours and hours and years in the lab just collecting all of that data and doing that processing. Obviously, nobody wants to do that. So actually, we found like a pretty clever way of like addressing that issue by actually using and borrowing images from like completely different scientific domains. So in our case, we use like the COCO image database that has like, you can see it has like pictures of dogs, birds, cars, everything, and make them look like AFM images. Okay, and there's like two benefits associated with this. The first one is if you look at like the composition of like images that we have, they contain like many different types of like features in terms of like complexity of lines, etc., which probably you're going to find in any sample that you're going to be scanning. Okay, and the second benefit associated with this is like now I have like a crap ton of data, which again, you would not be able to acquire in the lab doing just AFM. And so the idea is like you take these like natural images and you make them look like an AFM image. And so here are examples of like some of the things that we've been doing is now you can really play with like the different types of corruptions that you have. So like, misalignment. So you can see you have like, the image is like a little bit misaligned. You have like plane error. So like, a little bit of like the images would look like this. You have this like line scars I was showing you before. You have this like spot scars. You also have like this like polynomial error. So think about like curvature effect on your sample. And so if you know how to like basically extract these errors, you can apply them to like any natural image. You can apply them in sequence. You can also apply them in composition. And what we did was we basically did exactly this on this like set of like 250,000 images, including 2,000 plus corruptions. We basically ended up with like 2.5 million AFM-like images. Just to put that number in perspective, these, by the way, are like some of the images that we took in the lab. For us to took 2.5 million images, it would have taken us 30 years to get to that number. 30 years, 24/7 in the lab. And here in just a matter of like 6 days, we're able to kind of like generate that very large data set, okay? And then we use that like large data set trained with like a classical image corruption neural network. Again, UNet tends to be like my favorite network for this. And this is the type of results that you get. So here's an example where we took like a raw scan of like an AFM standard. This is the clean scan that you would get if you were like, doing it manually, slowly. And this is the reconstructed scan that you get as you pass it through what we call like AFMNet. Okay, again, trained on these like 2.5 million images. And the way you use that in like metrology is like because you want to use that to kind of like, measure heights of like these pillars, for example. That's how sometimes you calibrate your AFM. And what you see in terms of like the prediction of the heights between the clean target and the reconstructed height that we get from our AFMNet neural network, it's doing really good. It's doing really good to the point like we are within the uncertainty associated with like the measurement itself. Okay. What this is not showing you is like the amount of time that we saved. We started from just like the raw input for us to kind of like, take the raw input, do the clean target, do the height measurements. It takes you about 30 minutes. By taking the raw input, fitting into the AFMNet and getting these types of measurements, it takes you less than a second. Okay, so like in terms of like the amount of time that you save, you as a microscopist, now you can do a lot more data analysis as opposed to like data cleanup and data acquisition. We also apply that to like other types of technology. So we partner with a company called ASISPI. They developed this like AFM on a chip. And what they're interested in their case is like they can do like basically AFM scans on like very large wafers and very large areas. Okay. And in their case, they don't talk about scan speed. They talk about like, this like dwell time, but that you can transfer into like scan speed. And again, these are like the type of data that they collect. Okay. So they tend to be like, relatively dirty. You can pass that through our AFMNet architecture, or you can do like the data cleaning. And when you do like, again, height measurements, what you see is like we get like very, very good agreement with like what any user would do. And the other thing that like you should point out is we use like different types of like perceptual loss function. So in terms of like sharpness, clarity, and definition. In this case, the images produced by our AFMNet are even cleaner and sharper and more defined than like what you would get with like the classical like human treatment of this data. How am I doing in terms of time? I'm good? All right. Okay. Good. All right. So the last topic I wanted to cover, I'll try to be relatively quick, is how we can basically embed, again, our expertise to discover novel materials. So in this example, we're interested in like basically discovering novel MOF structures. So MOF stands for like metal organic framework, where you have basically these like atoms, linked with like different types of ligands, and people in chemistry use that for capture, chemical capture. Okay, and in our case, we're interested in like discovering certain MOF structures that are going to be extremely selective. Okay, especially when they're like extremely selective when you're trying to capture one type of molecule compared to the other, but these two molecules are very comparable to one another. So in terms of capture, it's hard. The challenge associated with like discovery of novel microstructures is that the design space is really big, and it's kind of like trying to find like a needle in a haystack. Okay, so how can we do this? So at a very high level, the best way you can do is like trying to like encode as much information as you can about this microstructure. If you look at the way people are doing into the literature, most of the time people are using just like a tabulation to describe this type of microstructure. Maybe in terms of like their volumes, maybe in terms of like the number of atoms, maybe in like the size of these pores, but actually we can do better. Okay, so if you just do a tabulated featurization of those molecules, you're going to be fairly limited in terms of like trying to find, you know, this like golden nugget into like this like vast sea of possible microstructure. So in our case, what we did was we came up with like a graph neural network representation of those molecules, where the global feature associated with like the graph neural network is like what everybody else is doing. Okay. And then we define two additional types of features. So the nodes are basically attributes that we define with like every single atom in those molecules. And the edges are basically features that are shared between nodes. So you can think about like, you know, number of neighbors. You can think about the volume associated with like an individual atom compared to its neighbor, etc. Okay, the connectivity between the different atoms, etc. And then we use this like graph neural network architecture into like a very classical optimization workflow. So we took our graph neural network, we used that as an input into like a classical feed-forward neural network, where the feed-forward neural network is going to basically predict absorption property. So chemists would call that like a Henry coefficient, okay? And the output of that neural network is going to predict the mean absorption property and some deviation. Okay, so you would get some like prediction, and it's gonna do that for like maybe just like one molecule at a time, or you can do it for like 2 molecules at a time, 3, 4, 5. You see, I talk about like multiple objectives. But these neural networks are like very easy to construct, and then you can use that in a very classical Bayesian optimization workflow to start, you know, doing the discovery process. So how does it work? So here I'm showing you an example of like some of the predictions from like the feed-forward neural network, trying to predict the absorption property for like one propanol. And you see we have like, you know, very, very good correlation. Same thing here, I'm showing you, you know, predictions for like butane, which is very close to like one propanol, but it's a different species. And it's like, you know, it's capture property. So this is basically to show you that like the feed-forward neural network is very good at like predicting absorption properties for those molecules. So then that gives us confidence like we could use that into our Bayesian optimization workflow to start doing a discovery. And so these are some of the results that you get. So here's a typical Bayesian optimization results where as a number of samples that you sample into your database, in our case, we use like a pre-existing database, which is called like ArcMof, that we use to train our neural network. And what you see is that, you know, using our GNN featurization, we can basically get to like the best solution very, very quickly within like 800, you know, sampled in our database, which does much better than like, you know, classical like Gaussian process, or that obviously much better than like, you know, just like some random selection. And that statement is true is even if I'm trying to do like, you know, predictions for like Henry coefficient, if I just want to do selectivity for like one species, or if I want to do for like 2 objectives. So for example, like one propanol and butane. So this is like when you start having like, you know, selectivity between one molecule versus the other, 3 and 4. So again, the take-home message from this is like by encoding a lot more information into the graph neural network compared to like what you would do with like a classical Gaussian process, you're basically able to capture a lot more physics, a lot more description of those molecules that you would do otherwise. So in conclusion, and because I knew there was going to be a lot of like postdocs and PhD students, I kind of like wanted to like relay that quote from Jensen Huang. He's the CEO of NVIDIA. And earlier this year, he was interviewed by a journalist who was asking him, what would you tell to your younger self going to a grad school? And his quote was like, for like the young 20-year-old Jensen that graduated now, he probably would have chosen more of the physical science than software sciences. And again, some of the examples I showed you is an exact illustration of this. I'm not a computer scientist, far from it. But, you know, I was trained classically in material science and physics. And by embedding those concepts, now you have like so many tools that you can use to code with like, PyTorch, and it's becoming easier by the day. This is where we add value, adding the physics directly into these types of neural network. So in conclusion, there's like really like 3 take-home message that you guys should like, take home with you. How do we teach and this like machine learning framework to be more appropriate to like what we do on a day-to-day basis? And so the 3 examples I kind of like showed you, one was like you can embed the physics directly into the neural network. So that was the example with like the super resolution, or trying to like predict uncertainty response from like this like 3D printed sample. You can mimic the physics. So that was the example with like AFM, where here we took images that had like nothing to do with AFM and made them look like AFM. Or you can spend some time trying to really think about how you want to represent the physics to get much better predictions that you would do before. So with this, if you have any question, feel free to shoot me an email, and I'd be more than happy to chat with you guys. Thank you.
Great talk. Thank you. Any questions?
Thank you for the nice presentation. I really enjoyed it. I have a question for both of these 3 programs presented. The first question is about the last one, which is a way to embed molecules to neural network. So you mentioned that you moved from traditional method, which is feature engineering, traditional feature engineering, into presenting molecule as a graph, right?
Yes.
So this is so clever. We kind of preserve a lot of information, but at the same time, you're making it complex and somehow impossible to interpret the results.
Okay, that's a good one. I'm going to push back. No, it's not necessarily more complex, because actually you can interrogate your GNN either at like the highest level, which is just like your global features, and your global feature is just going to look like an array of like properties. So it's a simple vector where you have like access to like interpretable data that like you and I can comprehend. You can also interrogate the GNN at the edge level, and if you, because the way you construct your GNN, you're saying you add as many features as you want to the edge. So in our case, we looked at like the volume between of one atom compared to the other, the number of neighbors, the area of like because just go back. Okay. So at the edge level, again, you can easily imagine like for like each atom, you're going to define some like volume that's going to be unique to it. That volume is going to have a shape. Each facet is going to have like some area. So all of these is like basically features that you add at the edge level. And then you can also interrogate not only at the global level, at the edge level, you can also interrogate it at the node level. And at the node level, this is information associated with the atoms themselves. So every information and features that you add at the node levels are, again, interpretable. So it is complex in the sense that you have like multiple levels at which you can interrogate your graph neural network. One of the things I didn't show, actually, we also did like ablation techniques, and we also did like global sensitivity analysis to kind of like discover and understand what are the features as captured by the graph itself that affects the most selectivity, especially if you want to predict or discover molecules that have like high selectivity between 1-propanol, 2-propanol, butane, and propane. So actually, it is a lot more interpretable because now you have access to a lot more information. So you're right, it's more complex because you have a lot more information. But in this case, you also have now more information that you can access that you didn't know about before. And therefore, it kind of like helps you maybe to spend more time in terms of like discovering or doing synthesis on, in this case, like, MOF that have like very, very specific attributes in terms of the geometry and stuff like that. And so where we're moving forward with this is like, now we can work with like chemists and tell them like, look, we think that like the best selective molecules, like in this case, is between like 1-propanol and propane, that have like this type of attributes. I'm not a chemist, but they can say, oh, I think I know how to like, get to that type of molecules. We can do XYZ type of process. And I was able to give them that instructions because I was able to kind of like interrogate the GNN, look at like all the features that we think are important and report back to the chemist. Hopefully I answered your question.
Yeah, I didn't know that.
Yeah. Sure, there's a question in the back and then maybe we can come back here, sorry.
Yeah, so,
The issue is that you have to, each degree of freedom adds exponentially
Yeah.
to the number of
Yeah.
simulation parameters.
Yeah.
So how does this show up in your approach?
That's a great question.
More complicated or
No, so actually, I didn't want to spend too much time on this because we cheated a little bit, meaning there was like already like very large databases of like MOFs. In this work, what we really wanted to demonstrate is like you can use GNN as an efficient way to kind of like featureize these types of molecules to do the discovery of like, highly selected MOFs, basically. But we didn't do any of the calculations that you're talking about because these take time. And so where we're moving next, actually, and actually we talked about this at lunch with Matthias, is now we're trying to like develop basically like diffusion models that can rapidly generate new structures that we can feed into our GNN, that we can feed into our Bayesian optimization, and hopefully then people can synthesize. So that's the first thing we're doing. The second thing that we're doing is all of this is like it's nice, but it's also, I would argue, working a little bit in a vacuum, meaning that work is primarily computationally driven. I didn't show you any experimental results. I didn't show you experimental results for like a very good reasons because we don't have them. But where we're moving next actually is like at Sandia, we have like a synthesis route, which is called like the Big Kahuna. So think about like basically like an automated platform to do rapid synthesis of like different types of molecules. And what we want to do is like basically start to link, and that goes back to the first question, is basically link the interpretation of those molecules as graph with like what you can measure experimentally. What you can measure experimentally in terms of like, spectroscopy data, for example, diffraction data, chemical signatures, etc. Because as soon as you know that mapping between your interpretable model of that molecule with like what you can measure experimentally, then it makes it very easy for us to kind of like just unroll that workflow to start doing the discovery almost on the fly as they're doing the experiment. Hopefully answer your question. Actually, no, we're going to use those diffusion models that I was telling you about. So, but I think it's fine to live with like approximation when it comes to like discovery. I would argue it's fine. As long as I have like 95% accuracy, I'll be very happy because the truth is only going to come from the experiments, right? At the end of the day, you want to, I don't necessarily want to have like the most accurate prediction. I want to make like the best molecule I can get out there.
And so I was just wondering for the kind of second application.
Sure.
Right? As I'm sure you know, a lot of the defects in the images.
In this one?
Yes.
Okay.
A lot of the defects in the images arise from oftentimes interactions between the features on the sample, the detector system, things like this, right? So in SEM, you get blowouts in contrast, in contrast from the response of the ETD. In AFM, you get it from rapid changes in topology, things like this. So topography, sorry. So my question is it okay that you essentially have created an agnostic layer of noise on top, or does that actually maybe introduce some artifacts because it doesn't know anything about the underlying physics of the interactions?
Yeah, good one. So actually, a lot of like the corruptions that we apply to our natural images, actually they've been extracted from actual experimental data.
Right, but I'm saying the features in the image don't correspond to the errors in the corruption layer, right? Whereas in real data, the errors in the corruption layer often are correlated to.
Yeah. So no, we haven't accounted for this, but everything that we've done worked extremely well for AFM data. Now we're thinking of like applying this for EBSD data that you use to kind of like, measure crystallographic orientation, which also comes with like its bag of complication. We would like to like apply it to like also SEM data. And, again, at that point, it means we're going to have to like rethink the way we do those corruption. But, again, the take-home message from this is, the major bottleneck as to like why people tend to drag their feet, and there's not that many publications actually right now in terms of like doing this type of exercise when it comes to like microscopy. It's because the bottleneck is it's going to take you forever to take any sizable training data set. Mm-hmm. And so here what we wanted to demonstrate is like we can start with like something that's has nothing to do with AFM, nothing. And then make it like, AFM like. You can always improve what we did, that's for sure. And if you have ideas, I would love to hear your ideas on like how to improve what we're doing. But the idea is like it's overcoming that bottleneck in terms of like data generation that you use for training from something that has nothing to do. But if you start thinking and looks like you're already starting to think about it, which is great, and which was the intent of that talk. But you can start with like something like this and like, what, if I want to make it like the data looks like, actually there's like a path forward. I just have to like think carefully on like how I can do it. Exactly. Yeah, you can use whatever model you think is appropriate to kind of like incorporate, more and more physical description into it. So again, what we've done is still, I would say, like, very simple. Another thing I didn't talk about is, turns out we had to be a little bit careful in terms of like the sequence in which we added the different errors to our composed image. Because some of them were kind of like double counting the errors, or like they were like, washing out some of the errors that we really wanted the neural network to learn. Again, the exercise is this one, right? You want the neural network just to learn that veil out of like, the clean target. Because you're saying the underlying image is defect free. But how you do it, there's like, right now there's still like a little bit of like an art to it. Again, I don't pretend we did it the best, but at least we have like a path forward to kind of like applying it to like many microscopy techniques that we care about. Hopefully I answered your question.
In that same context, but actually we tried something not the same but similar years ago with secondary electron images and images. And the idea was also to say, well, there is what you call corruption, something not looking nice. You want the image to look nice. What's with it? The problem with that one was that things that were real, which looked like corruption, were then also cleaned, when indeed it existed on the sample.
Yeah.
How can you avoid that one?
That is
typically that's what people want to see. So where they want
so that's
a quality check, and you want to check whether your sample is clean.
Yeah.
And with these methods, they always look clean, and you're always happy.
Yeah.
In fact, they are not.
So that's a tough one. Actually, we encountered that very specific issue with the work with like IC-SPY. So these images are actually like of some like membrane, a biological membrane that they work with at the University of Toronto. And so obviously here, again, I'm cheating a little bit. I'm showing you guys my best results. But we did have this problem, like some of these images where it was clear that like our AFM net was kind of like removing some of these actual, defects that you want to see. And the way you can potentially identify those is by basically looking at like anomalies, especially if you apply to like many different types of images. Again, we haven't been like 100% successful, but like anomaly detection is potentially one way of doing this. We also apply, I'm not showing you the results in this presentation, but we applied also that technique with STM data. And in this case, what they care about is actually counting the number of like vacancies they have in the samples that they're measuring. And in our case, what we did for the STM data, we went back to, we could not apply our FM net directly. We had to remove some of the errors that we think like the network is going to start to, interpret as like being corruption in the image, when actually we're like, no, these are actual features. So there's also a choice that you have to make as a user when you build your neural network, in terms of like making sure that like, the composition of errors that you use to train your network is not going to start, removing some of the features that you want. But again, at this point, we're still making like baby steps. But when we worked with like STM data, for example, like spot scars type of like features was not part of like the training data. Before I answer your question, yeah.
Thank you, Rémi.
Right.
Again, reminder. If the composers can also really remove the data. Don't forget to start in the sheets if you haven't done so. How does it compare with the simulation?
What is this method? Which method? The FM data or?